Well, here's 2015 number 3. I would like to claim that I have taught you all of the things that could possibly come up on this exam of mechanics. And when they threw this out in 2015, my students became clear to them that that claim was false. So part A here, they're asking you to do something that we never did in class, which was to actually use the rotational inertia is equal to the integral r squared dm. We never actually did an integral like that. We just kind of learned some different rotational inertias. It's pretty complicated, and it very quickly gets into multivariable, like a third semester calculus beyond what we did this year, unless you have very simple things like thin rods. So let me show you how this works, and you can decide what you want to do with that. So here's our rod. It has a mass of m and a length L. The reason that the thin rod is really the simplest example to use is because if you imagine like a tiny little piece of the rod that has an infinitesimal mass like dm, kind of like delta m, but the delta has approached, we're letting it approach 0, then the amount of mass is directly proportional to the amount of L that you have. So what that means very simply is that the ratio of the whole mass to the length is equal to dm over dl. As soon as you get into things like cylinders and spheres, this relationship is much more complicated, and you have to get into the density of it, and the cross sections are different sizes, and it's just a complete mess. But here, solving this for dm, the key to being able to do this integral is understanding that you can make this substitution here. And if you're wondering, well, how the heck is that going to help? Because the r here is, those are L values. Like the r we're talking about here with the length of a rod, it's how far away we are from the axis. So let me show you what that looks like. So r squared, my dm, I'm going to substitute here and call that m over L. And d length, that's really the same as dr, right? Because the length, really we're talking about r values here. You could either call this dr or you could call this like a lowercase l. Now this is just a constant. And then where are we integrating from? Well, we need to integrate from where the r is equal to 0 to the very end of the rod where it's equal to L. So we're integrating from 0 to the whole end of the rod. So that's m over L. This is the calculus parts. Once you figure that out, calculus is easy. The antiderivative of r squared is r cubed over 3 from 0 to L. And then plugging in the L here, I get mL cubed over L times 3. Plug the 0 and you just get 0. One of the L's cancels, and you get mL squared over 3. Now that's what they're looking for there. And boy, was I surprised when they threw that out there. I mean, that's on the formula sheet and everything, but I never really expected that they would ask you to do the integration there. And they can really only ever ask that with a thin rod. If you're interested in seeing if you understand that, you could try to prove using exactly the same kind of calculus here that we did. You could try to show that the rotational inertia of a rod about the center is 1/12 ml squared, and think about like the R would, in that case, would only go from 0 to L over 2, but because of the symmetry of it, well, I'll let you try to figure that out. And if you try that and you're interested and you get it, that's great. And if you don't, you can come ask me about that. I would not expect to see that again. That was a surprise. All right, part B. We know how to do this. Derive an expression for the velocity of the free end of the rod at position B. So it's going to go from here and fall all the way down to here. This is an energy problem. You can't use angular rotational kinematics because the acceleration is not constant. This thing is experiencing an angular acceleration because of the torque from gravity. And as soon as it starts to rotate, the angle of that force, the angle between the force and the R, starts to change, so it's not constant angular acceleration. So you must use energy considerations. So at the top, it's got gravitational potential energy, and at the bottom, it has rotational, sorry, did I say gravitational potential? I think I did. And here it's got rotational kinetic. So let's see. This is capital M, G, and the H here, you got to be real careful what the H is. This is the height change of the center of mass. I'll come back to that in a sec. And then that's equal to 1/2 I omega squared. So let's see what we can do with that. So that's mg, the height change of the center of mass. This is the center of mass, right in the middle of the rod. And that's going to go down to here. So that height change is actually L over 2. It's not L. In rotational problems, so often that distance we're looking for is the distance from the axis to the center of mass. That is the case here. That's 1/2, and then I is 1/3 ml squared. And we want the speed of the end of the rod. No, so omega is equal to V over R, and at the end of the rod, that is a full distance L that we're interested in, right? We're interested in the very end of the rod, which is a distance L. All right, let's see if we can't simplify this. Let's see, the 1/2s cancel, the M's cancel, all of the L's cancel on this side, leaving on this side, it looks like I would have GL. And then on this side, my 1/2 canceled, I still have the 1/3. And my L's cancel, my M canceled, so I have the V squared. I think I'm doing okay here, so V would be equal to the square root of 3GL. Just took a peek at the scoring guide there, that's correct. Just want to make sure I didn't send you off in the wrong direction there. Okay, so now let's see. An experiment's designed to test the validity of the expression found in part B, so to see if this is true or not. And so we have an expression here which V equals something L. So there's a couple ways you could go to graph stuff to try to get a straight line. And yeah, in part C, that's what they want. They want to know what should be graphed to give us a straight line. There's two ways you could go. You could make a graph of V versus the square root of L, right? And then the slope of that line would be the square root of 3G. Or you could do V squared versus L, right? If you square both sides of that, you'd get the expression v squared is equal to 3gl. If you graphed v squared versus l, then you would get a line, the slope of which should be 3g. So you can do either one of those. It's up to you. And I guess they had a little, like, what should be. So this is our horizontal axis, would be one of these. Vertical axis. And I think that they actually, let me look at this going back real quick. I think they should take them either way because, because either way you're going to get a straight line. So any combination of these things or these things in those two blanks would get you the all of 1 point there. Now, I am not going to graph this by hand because I don't feel like it. But I am going to go ahead and find the v squared values. So those, and then I'm just going to do the graph in my calculator. You will do it by hand and pick a couple points on that line and find that slope by hand. That's what we would like to see. But I don't have a copy of the graph. That's why I'm being lazy there. Sorry about that. It's not just like some kind of endemic laziness. It's more acute situational laziness. But I am going to need these values. So 2.7 squared. And I'm going to stick to 2 sig figs here. Oops, 3.8 is equal to 3.8. Go figure. 3.8, that's 14, and 4.6, and 5.2, and 5.8, and 6.3. Okay, I'm going to go to my stat menu and go ahead and put in L1 the lengths, so 0.25 and 0.5, 0.75, 1, 1.25, and 0.5. Oops. 1.5 rather. And here I've got my 7.3, 14, 21, 27, 30, 4, and 40. And I'd like to know what the line of best fit for that is. So I'm going to go to Stat, calculate the linear regression for that. And it looks like I've got a line that, now my line's going to be of the form v squared equals slope times L. So that gives me v squared is equal to the slope, which looks like my slope is about 26 times L. And I have a small intercept here. If you drew yours by hand, you might have made it more or less go through the origin. I'm going to go ahead and just assume mine goes through close enough. Mine is, it's about 0.9. We really should have the right units here. So units of slope are units of rise over units of run. Right, so that would simplify to meters per second squared. And let's see where we are in the problem here. So you plot that, make sure you got all your axes. They left it wide open for you for scaling and axis labeling. And using my straight line, determine the experimental value for G. So if v squared is equal to 26 meters per second squared times L, this 3g is equal to 26 meters per second squared, right? That's my slope, so I set those equal. So my experimental value for g is 26 divided by 3, which is 8.7. So, I mean, yeah, it's kind of, ballpark-ish, I guess, right? And then that's E part 1. And then in E part 2, they want to know, describe 2 ways in which the effects of air resistance could be reduced. Well, the first thing that I would think of would be to use small displacements. Because if you use small displacements of the bar, you'd have lower velocity, which means you'd have lower air resistance. That's the first thing that I would think of. The other one, I'm looking at their scoring guide here. There's a few different things that they suggest. I think, honestly, if I saw this, I would think the first one would seem pretty obvious to me, that you just want to get it going slower. So other ones like do the experiment in a vacuum is one of their suggestions. That seems a little bit, expensive, let's say. Use shorter rod lengths. Less rod would mean less rod to crash into the air. More dense rods. Use a more aerodynamic shape for the rod. Something that would slice through the air more easily. So any of those are okay. Let's go with do it in a vacuum. That sounds fun, right? Oops, sorry, there's only one C there. All right, there you go.